Welcome back to The Explainer. So, let's dive right into what I think is a truly fascinating paradox in the AI world. We're constantly bombarded with headlines about AI systems acing bar exams or solving complex logic puzzles, right? On paper, they look absolutely brilliant. But what if I told you that some of these top-performing models are secretly cheating? Yeah, literally cheating. Today, we're looking at a groundbreaking paper that peels back the curtain on AI causal reasoning. It reveals how these models can completely fake their intelligence, and more importantly, how researchers have finally found a mathematical way to force them to actually think. Okay, 73.9%. That is the exact number that kicked off this entire mystery. During some recent experiments, researchers took a 270 million parameter model, specifically Gemma, and fine-tuned it on a highly complex causal reasoning test called D-separation. And when the results came back, the model hit a wildly impressive 73.9% accuracy. In the AI space, that's a really solid passing grade. Usually, at that point, you'd pop the champagne, publish the paper, and declare that your AI has successfully mastered cause and effect. But hold on, because this perfectly illustrates a massive blind spot in how we evaluate AI right now. It forces us to step back and ask a really critical question. Is this AI actually smart, or is it just a remarkably good guesser? The thing about high accuracy scores is that they can be incredibly misleading. They tell us how often the model got the answer right, sure, but they tell us absolutely zero about how the model actually arrived at that answer. So to figure out what Gemma was doing behind the scenes, the researchers looked at another metric entirely. And here is the smoking gun, 7.6%. While the accuracy was nearly 74%, the model's F1 score, which, remember, measures the balance between precision and recall, was a downright dismal 7.6%. I mean, how is a gap like that even possible? Well, it turns out the AI hadn't learned a single thing about causal reasoning, not one bit. It hit that high accuracy by literally just guessing the word no almost 10,000 times in a row. It's basically that kid in high school bubbling in C for every single answer on a multiple choice test and just getting super lucky because the test happened to have a whole lot of C's. This exact catastrophic failure is what we call model collapse. In the world of causal reasoning, model collapse is a totally degenerate learning outcome. It essentially means the model completely ignores the actual logic or the structure of whatever prompts you give it and just converges on a single, fixed output. It either always says yes or always says no. And honestly, here's the truly terrifying part of the paper. The researchers found that when you try standard fine-tuning on these causal reasoning tasks, this collapse happens with a 100% failure rate, literally every single time. So, to definitively prove this was happening, the researchers ran the Gemma 270M model through two very specific causal logic tests based on Judea Pearl's famous framework. First up is transitivity. This one's pretty straightforward. If A causes B and B causes C, does A cause C? The second is D-separation. This is a bit more complex. It asks if two variables, X and Y, are independent from each other if we already know a third variable, Z. These are the absolute foundational logic puzzles for any causal system. The proof of this collapse is just striking when you look at the results for the transitivity task. There is just this solid green wall of data that represents 10,000 blind yes predictions across every single test category. Whether the researchers made the logic chains super long, or reversed the edges, or shuffled the names around, the model just didn't care. It wasn't looking at the graph structure at all. It just blindly shouted yes 10,000 times in a row. And the D-separation task reveals the exact same vulnerability, just going in the opposite direction. This time, we see a massive wall of red, which represents blind no predictions. This completely exposes that initial 73.9% accuracy score we talked about earlier. It was a total illusion, guys. The dataset for this specific test naturally just had a ton of scenarios where no happened to be the correct answer. The model essentially just exploited a statistical bias in the test data. It figured out that blindly guessing no yielded the highest reward for the absolute lowest cognitive effort. So why exactly does standard AI training cause this to happen? Well, it all comes down to how the AI is graded. Standard fine-tuning uses something called cross-entropy loss. Cross-entropy really only looks at the final answer. If the answer is right, the model gets a reward, even if it just got lucky and guessed. To fix this, the researchers introduced a mathematical cure called semantic loss. Now, unlike cross-entropy, semantic loss doesn't just care about the final answer. It actually evaluates the logical path the AI took to get there. The crucial point here is understanding exactly what semantic loss is doing under the hood. Think of it as a really, really strict math teacher. It's a function that explicitly penalizes the AI for violating graph-based logical constraints during training. Meaning, if the model guesses yes, but can't mathematically prove the continuous path from cause to effect, semantic loss steps in and slaps it with a heavy penalty. It forcefully removes that statistical shortcut and demands, literally demands, that the AI traces the actual causal logic paths. But of course, there's a catch. You can't just slam the model with these incredibly strict logical constraints on day one of training. If you try that, the whole training process completely destabilizes. See, the standard cross-entropy loss is trying to teach the model basic grammar and patterns, while at the exact same time, the semantic loss is screaming at it about advanced causal graphs. Those conflicting signals cause catastrophic interference, and the model ends up failing to learn anything at all. To solve this bottleneck, the researchers invented a technique called dynamic lambda scheduling, and I absolutely love this concept because it perfectly mimics how human beings learn. Think of it like putting training wheels on a bicycle. In step 1, they start the semantic penalty incredibly low, at just 0.05. This lets the AI learn basic syntax and kind of loosely pedal around. Then in step 2, they gradually linearly tighten the rules. And finally, in step 3, they cap the penalty at 0.30, locking in that strict structural logic only after the model has found its balance. Their iterative development really proves why this dynamic ramp-up is absolutely essential. In version 2, they tried a weak fixed penalty of 0.05. Result, the model just ignored it and collapsed anyway. In version 3, they bumped it to a medium fixed penalty of 0.1. The model was stable, sure, but its reasoning was super weak on the complex tasks. It was really only in version 4, by dynamically shifting from 0.05 up to 0.30, that they achieved total success. The training wheels approach actually worked. The difference is just night and day when we look at the before and after. We go from that broken transitivity baseline, just a mindless, solid block of green yes guesses, to the fully trained semantic version 4 model, which is this beautifully balanced, context-dependent distribution. The semantic model is dynamically predicting yes and no in perfect proportion to the actual logic of the unique tests it's being given. For the first time, it is actually thinking. And if we really want to prove the AI isn't just guessing anymore, we just have to look at the branching task. This is where the causal graph gets messy and splits into multiple complex directions. The collapsed baseline model, it scored a horrific 1.96% on this task. But with dynamic semantic loss, that accuracy absolutely skyrockets to 97.9%. That is a massive breakthrough metric. It proves without a doubt that the AI has genuinely learned how to navigate highly complex branching causal structures. Now, of course, in science, you have to prove your success wasn't just a weird fluke. So the researchers threw an adversarial gauntlet at their new model. They built a stress test of 1,000 tricky, confusing causal graphs designed specifically to fool an AI. They threw in irrelevant nodes to test if it gets distracted. They included broken chains to see if the AI would hallucinate missing links. And they used these super long chains to really test its extreme multi-hop reasoning capabilities. The results of this adversarial gauntlet are incredibly revealing. The deseparation baseline collapse model failed spectacularly, dropping down to 43%, which, by the way, is literally worse than a random coin flip. Meanwhile, our semantic models maintained really strong, consistent performance between 67 and 70%. They successfully navigated the traps, proving genuine structural reasoning. But you might notice something interesting in the middle there. The standard pre-trained Gemma model scored 66.7%. Now, that 66.7% for the standard model might actually look pretty good at first glance. But as the researchers point out, standard Gemma uses task-specific heuristics, not structural causal reasoning. Essentially, the massive pre-trained model is just using superficial pattern matching. It's read so much of the internet that it recognizes the shape of the question and makes a highly educated guess based on that, but it isn't actually tracing the causal graph at all, which highlights exactly why the semantic fine-tuning fix is so deeply critical. So what should you take away from all of this? Well, the key insight from this entire explainer is that implementing semantic loss with dynamic scheduling isn't just some optional optimization to make a model slightly better. It's a mandatory guardrail. Standard causal fine-tuning is fundamentally broken and practically guarantees a 100% collapse rate. Semantic loss is the vital bridge that transforms that broken process into reliably stable, genuine AI reasoning. Which leaves us with a final, kind of provocative thought. If a top-tier model like Gemma can easily fake a 74% passing grade on a logic test just by blindly guessing no 10,000 times, what else are these models faking? What other critical AI tasks out there in the real world, whether that's in medicine, finance, or law, might be hiding collapsed reasoning behind high accuracy scores? It is a huge question the tech industry urgently needs to answer as we continue pushing the boundaries of AI. Thanks so much for joining me on this deep dive into the illusion of intelligence, and I'll see you in the next explainer.